Okay, so let's continue. We've got projectile motion. Uh, so, you have to break the problem into x and y coordinates, right? So typically a person would do something like this. And then they've got a projectile that does something like that. There's the top. This is the range. We had an initial velocity that started us out with some angle theta. And so in the x direction, we don't have much to do because ax equals 0. I mean, unless somebody says ax is not equal to 0 and there's some slowing down due to friction, drag, or whatever, then fine. But that leaves you with not a lot, right? I mean, basically, anytime you want to check out what your x at any time velocity is, well, you've already figured it out from your v naught x, which happens to be v naught times the cosine of theta. So fine, the distance x that you travel is also, let's do delta x is equal to v naught x times t. And that's it. In the y direction, it's a little bit more complicated. Which one of these do I want to do? Vy. Let's get rid of that. Vy, of course, is v naught y minus gt. That's minus gt because I'm saying that up is positive. So we've got up positive. We have to make minus g. It's a vector. It's pointing down. Everyone knows that. So then we have our delta y is equal to our v naught times t, v naught y times t. And then again, we're doing a minus gt squared. One other equation, we could have vy at any point is equal to v naught y squared minus, again, it's minus. Why is it minus? Because g points down. And that all times delta y. So those are our equations of motion for projectile motion. So I'm going to link them. Equations of motion for a projectile. Okay, now honestly, if you need to solve for t, do stuff like this. Use the x direction as much as possible. If you have to solve for t and all you have is this, then you end up with a quadratic equation. And, you just got to bite the bullet. If you're trying to solve for heights or other things, I would do this equation or this equation. So it all depends on what it is that you're trying to do. And then you have to do the algebra. I mean, algebra is a thing, and you're going to have to do the algebra to get it back, to get what you want. Okay, so let's move on to forces. And, man, I mean, F equals ma is really, really powerful. What is that law? That's Newton's second law. And these kinds of things are easy to make multiple choice questions, right? So knowing Newton's first, second, and third laws and the universal law of gravitation, those would probably be helpful because it's a big deal. Conservation laws you want to know, that kind of stuff. Okay, so what are we dealing with? We could have static situations where F net is equal to 0. But what is F net? F net is equal to the sum of all forces acting on the object. So here's our object. We have a bunch of forces. 1, 2, 3, 4. Let's put a gravity in there. Okay, so we've got all these forces. What does that mean? Well, we decide what's up and what's down and what's positive and negative or whatever. Like maybe we do something like this, positive x, positive y. And then we have to break all those forces up into the x and y components and add them together. So in the end, we would end up with like the sum of the forces in the x direction equal to 0, and that would be f1x plus f2x plus f3x plus f4x, f5x, okay? And all of these have an angle, right? There's an angle here for each one. And all you got to do is figure out the x component of these things. You do that and you add all those things up, and one of them is something that you're looking for. You're going to do the same for the y direction. That's a 4. The 4 caught me. Okay. So, fine. That's static, right? Because we've got this, which also happens to be the first condition for equilibrium. Okay, so static in the force direction. All right, so what do we have next? Next, we would have a dynamic situation where our F net is not equal to 0. It's the mass, whatever the mass of the object is. That thing has a mass, times the net acceleration. And it'll have an acceleration. So all those forces add up to some movement where the actual thing moves, okay? Then it's a different story. Then we're going to be doing some of the forces in the x direction equals m times a net in the x direction. I'm just going to put ax here, okay? You can call it net ax. You can call it whatever you want. But that's going to be equal to all the same things that we did before up above. This dot, dot, dot just represents 2, 3, 4. Makes it easier to write out. And you do it for the y direction. And once you have your AY and your AX, you can do your AX squared plus AY squared square root. Again, the Pythagorean theorem. That'll give you the A net. But what does it give you? It gives you the absolute value, right? You get the absolute value of a vector, okay? So you have your absolute value. But what if you're asked for the vector? Well, you got to get an angle in there. So the angle for that vector, let's call it theta, would be, and we can draw theta right here. Okay. And that would be with respect to the x-axis, and so therefore we're going to take AY and we're going to divide by AX, and then we're good, because then x is in the denominator, and then we have it with respect to the x-axis, positive x-axis. Okay, so static and dynamic, or kinetic, you can call it kinetic if you want, but dynamic's a better word. Okay, so let's talk a little bit about inertia. And hopefully you guys know why I'm going to talk about inertia, because what are we talking about? Newton's laws, and Newton's first law is inertia. So an object at rest wants to stay at rest. Now, do objects want things? I don't know. They just don't want to move. So they're massive. It's hard to move them. They want to sit still. Why do they want to sit still? Well, that's a deeper question that I'll answer. I'll tell you all about it if you want, but you got to ask me. Okay, so an object at rest wants to stay still. Okay, what does stay still mean? It means that you can't you can only accelerate the object if you apply APPLY a force to it. All right, so it'll stay at rest until you apply a force to it, and if you can get it a force applied to it, then here you have your mass, you apply a force applied, and then that thing will start to accelerate in the same direction as the force. Fine. All right, great. You guys know this, that's fine. The more massive it is, the lower it wants to accelerate, the slower it wants to accelerate. So we can see that it's directly proportional to the force applied and indirectly proportional to the mass. So if the mass is super, super big and your force, you're trying to push on a boulder or something, you're not going anywhere with that thing because it's just too massive, and it's not going to work out. So large objects, heavy objects don't want to move. Now, there's one other aspect to this. Acceleration means a change in velocity. So a change in velocity means v final minus v initial is not 0. All right? So there's a difference between them. In other words, delta v is not 0. But v final could equal v initial, and you would still have this same situation. So what that means is your mass could have a velocity, but the velocity is constant, and we still consider that staying still. Okay, it is not moving it's not accelerating. So there's no dynamics to this situation. All right. It's, or there's no, yeah, A not equal to 0 means dynamic. So it's definitely not static, but it's not dynamic either. So we could say that it's kinetic. So this is where kinetic comes in. And I'm going to erase kinetic from up above because that wasn't really the best use of kinetic. This is kinetic because we're just moving, but we're not accelerating. There's no dynamics to the situation. Okay, so that's Newton's first law. Oh, don't want that. Newton's second law we already talked about. Before we move on, though, Newton's first law also has a rotational component. And rotationally, so here's our object. Maybe it's full of stuff, whatever, and it has some radius. Some radius r, and it has a moment of inertia. The moment of inertia is the rotational equivalent of mass. Okay, so on one hand you have the linear situation of mass. Over here you have rotational moment of inertia. Okay, and then this thing is going to be moving in a circle. We talked about Newton's second law above linearly, but rotationally, the second law is torque equals I alpha. All right, so instead of M, we're putting in I. And instead of acceleration, we're putting in alpha. And we all know that if you multiply r times alpha, you get the acceleration. Okay, so at any point, if I wanted to know what the acceleration is here, I just have to know what this tiny distance here is. Okay, so there are different accelerations depending on how far away from the rotational pivot you are. So good. So that's the rotational second law. Now the third law. Newton's third law. The equal and opposite forces thing is most easily seen by having an object on a table and the object has some mass times gravity, but one object is pushing down, the other object is pushing up, and so we have a table and a box. Maybe it's Christmas time and there's a bunch of boxes on the table. And we've got a normal force, the table holding the box up, but the box does want to go down. But the normal force that the table is exerting on the box happens to be equal, they're equal and opposite. So because the box isn't moving, you can look at it like this. Box isn't moving. All the forces add to 0. We define one up and one down. Let's just make down positive. Let's do that. We'll get nutty with it. So down is positive, so mg minus the normal force. And that equals 0, so we see that the normal force is equal to mg. Equal and opposite, okay? That's the whole point. Equal and opposite. What does opposite mean? Opposite means it's pointing in the opposite direction, okay? Or it's negative to the other force, okay? Equal and opposite. So I talked about the first condition for equilibrium a second ago. Let's talk about the two conditions. So conditions for equilibrium. And we need two. So one, I said F equals ma. You can turn that into A equals F over m if you want. And you know that m isn't 0, so that's nice. We don't have to divide by 0. We're not Chuck Norris. Thank you very much. And so our acceleration is 0, okay, in equilibrium. So for that to be true, F has to equal 0, A has to equal 0. This is the more important one. And this, of course, is your net, right? Because it could be a whole bunch of forces applied. Those forces aren't 0, but the net force is. But A equals 0. That's the key, okay? And if A equals 0, then that means that A, since A is delta V over delta T, delta V must equal 0 as well. Well, delta V, we all know, is V final minus V initial. That equals 0. Then that means that V final equals V initial. Now, this could be 0, but it could also mean that V final is equal to a constant. Okay? Like a terminal velocity or something like that. All right. So if that's the case, if V final is equal to a constant, equal to V initial, equal to a constant, then you have a thing that is moving, kinetic, okay? But there's no dynamics. All right. Our second condition, torque, and I should be really putting net on this, is equal to I alpha, but it has to be 0. And again, we can put it in terms of torque and moment of inertia. The object has to have a moment of inertia because it's an object. I don't know what just happened there. It's an object, so it has to have a moment of inertia. So we're going to divide that moment of inertia into our torque, and we have to get 0. Okay, so again, our torque can be equal to 0. Our torque net is equal to 0. Our I can't be 0. And that requires alpha equal to 0. That's the important one. And we can do all the same stuff showing that delta omega is equal to 0. And you could have two different cases. You could have omega is equal to a constant, just like V was equal to a constant, or it's equal to 0. Okay? So those are conditions for equilibrium. What does equilibrium mean? It means static. Everything is static if you're in equilibrium. Okay? All right, let's move on. Weight and mass, I think you guys understand that. I never like to use W for weight. I never use W for weight. I always use mass times gravity. Mass often cancels out in your equations. So when you do the algebra, the mass will cancel out because it really doesn't matter how massive the object is in a lot of situations. So I don't like writing weight. If you're good with it, that's fine, but I'm not. So I use mg. I recommend you do too, but you know, whatever you guys do. You're smart people. You know how to handle this. The normal force, of course, is the best. Normal force is the prime example of Newton's third law. All right, so if you can understand the normal force, which we just talked about, then you understand Newton's third law pretty well. I'm not gonna I have it written down. It's in the notes. I'm not gonna go into that any further. Let's talk about tension. So tension is a flexible medium with a force moving through it. What do I mean by medium? It's the conduit. It's what the force travels through, okay? It's a flexible medium for force application. Okay, however, there's a tricky part about this. The flexible part means here's my rope or whatever it is. It could be a rope, it could be a chain, you know, ... whatever, all those things. Here I am putting a tension on it here, and here's my object over here. As soon as I put that tension on it, it's going to straighten out the rope, and I'm going to be able to move this massive object. I can pull that direction, but if I push in this direction, all it's going to do is wrinkle this thing up even more, or leave it behind or whatever, and you're getting nowhere. You're not going to get anything out of this. So you can't pull only, can't push, only pull. Okay? So that's all you need to know about tension, really. You guys understand tension pretty good, I think. So that leads us to friction. And there's different types of friction. And friction abounds. That's an N, by the way. If anyone's worried about that, it's an N. So here we have the force of friction. and it's equal to mu times the normal force. So we have a situation where we would maybe, I'm going to draw a little bit more complicated than what we have in the notes. So we have some box that can't roll. That's why it's a box, and I don't want to deal with rolling at the moment. And I've got a normal force. I've got mg sine theta. This one is mg cosine theta. And then, of course, we have something that is holding it back, and that is the force of friction. So to some people, you would say, oh, automatically, I know that the normal force is mg cosine theta. And if I slap a mu on the front of that, then I have my frictional force in this situation. That's great. All I did was break down mg into its different components, okay? It looks like mg sine theta was a little too long. So let's do that. So I just broke down mg into its sine theta and cosine theta. And of course, this is theta. Components. Okay. So we have our force of friction. And this is due to two objects touching, two surface objects touching. Okay. They're touching each other. Therefore, there's a normal force. So that's just touching. All right, and that's fine. Everything's great. Another thing to note is, well, there's a couple of things. The force of friction always, so this is number one, always opposes the movement. So if you've got something that wants to go in this direction or will be accelerated in that direction, the exact opposite direction is where your force of friction is going to go. Okay? All right. Always opposes the movement. The second thing is that it's always parallel to the surface. Okay? Always parallel to the surface of travel. Okay, so, and opposes, this pretty much also includes two, okay, because it's opposing. So no matter what happens, you have to have 180 degrees. If you're going to be moving in that direction, your force of friction goes in that direction. And that says the same thing, because you're not going to bounce up and down. You're going to slide down the surface, right? So if you're always opposing that movement, then it has to be parallel. So this we could call that 1, and this one like 1b or something. Just a little note. Okay, so there's a thing to keep in mind also. There's two different kinds. There's the kinetic friction, and then there's the static friction. And what I want you guys to know or remember is that kinetic is always less than your static, okay? So to stay still, to overcome the force of friction of staying still, you need more force. So the force applied has to be greater than or equal to your mu static times your normal force. All right, to get movement. Let's just say greater than. Okay. To get movement. And your force applied, once you have movement, your force applied has to be greater than your mu kinetic to maintain movement. All right, so you can get movement initially, and then you can maintain it once you have it. And that's where these two things come in, static and kinetic. All right, S for static, K for kinetic. You get it. All right, we're doing so good. Let's talk about drag forces. Okay, you go. Drag forces. Here's our force of drag. There's some constant. I'm going to call it K because C is a different thing. What is K? K is equal to 1/2 C rho A. C, what is C? That is your coefficient of friction for the items in the medium. In the medium. So it all comes down to what are the two mediums, what is the item, what is the medium that it's traveling through. That is your coefficient of friction. Rho. Rho is equal to, and you guys know this, we've been doing rho lately a lot, density of the medium or material that you're traveling through. And then A, of course, is the forward-facing area. Let's slide up. Area. Okay, forward-facing. Fine. But you guys, you know me. I'm not going to do probably, I don't know. But I'm probably not going to do any of those things. What I'm probably going to do is give you this, okay? And then, whoops, I dropped my squared. You're probably all screaming, you need to have a squared on there. I hope that's what you were doing. I'm going to do it better there. Okay, so I probably will just give you the K. But who knows? I don't know. Sometimes I say things and then I do something else. I don't know. So just keep this in mind. And then if you've got it on your cheat sheet, then you should be happy. So we've got this K, I'm calling it. In the notes, it's C, but whatever. I don't want to duplicate C. So let's talk about this for a second. If you're traveling at terminal velocity, so you're dropped out of an airplane, and the object is just going down, 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 down with a constant velocity because you're at terminal velocity, and you've got some mg pulling you down, then you can say my F net is equal to 0, right? So then that means that my force of friction, my force of drag, friction, is equal to mg, right? And now you can start saying, oh, well, that's kv squared, and all of a sudden everything gets really easy to solve, yeah? So this is, this right here is a really good equation to have. In the notes, I go through and I show that V then, of course, is your mg divided by k square root. Fine. These are equivalent equations, all right? One's one way and one's the other. Depends on what you want to solve for, all right? What if you want to solve for k? You can do it. I have faith in you. Okay, so we've done a lot of that. We've done all those things. Let's do rotations. Okay, rotations. Equations of motion for rotations I'm so good at this. Rotations. Equations of motion for rotations aren't going to change, right? What do we have? Instead of x, we've got theta. Instead of v, we've got omega. And instead of a, we've got alpha, right? And we can just start talking about what that is. If there's an acceleration, an angular acceleration, then delta omega or delta theta is equal to your omega initial times time plus 1/2 alpha t squared. If there is no alpha, then you're just left with omega t, right? So, great, that's easy. Delta omega, that's equal to alpha t, and alpha is given or you're trying to find it, right? But you could also say it's omega squared, omega final squared minus omega initial squared divided by 2 delta theta. Okay, what did I just do? I just wrote this equation in a different way. Which is the fourth equation that you need. Okay, so these equations of motion are the same, it's just the symbols change, right? Because you're rotating. So those are all there. I have a few more written down, and we can do something like, say, equals r times this, equals r times that, and equals r times that. You can do that. So all in all that stuff is golden. One of the things, and I didn't say this when we first started learning it, but due to conservation of momentum, linear momentum, should I say linear? Let's say linear. Linear momentum, we get a third acceleration when we're rotating. It's a linear acceleration, and it's always toward the center, and it's v squared over r, so whatever your velocity happens to be, divide by r. But your velocity is going to change depending on where you are in your radius. So the velocity here is different than the velocity here when you're traveling in a circle like this. So a better way to do it is to just take whatever the radius is and multiply it by your omega squared, because this omega is the same, but this v is smaller, v1 is smaller than v2. Okay, smaller than. That didn't work out because it looked like another v. But Let's do it. V1 is less than V2. Okay, so smaller than. But, and then you're like, oh, well, which radius do I use? And you're going to use the wrong radius and blah, 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 all the stuff. So this one isn't quite as good as this one, because this one, no matter what happens, no matter what the radius is, you've got your omega squared there, and you're going to get the right answer. Okay, so that's why I would use this for centripetal acceleration. Centripetal acceleration. And if you don't have something holding the object in place, so here we are swinging, I don't know, we've got something on a string and it's going in a circle, and there's a sharp sword right here and it cuts the string. Well, what's going to happen? That object is going to maintain its momentum. So P final will equal P initial, and that means that V, this is our V initial, the V initial will maintain itself, and here's our V final, and the actual object will spin off and go straight. Okay, so that's why conservation of linear momentum is what the object wants to do. But what are we forcing it to do? We're forcing it to have some kind of tension or some force here that's holding it in the circle. Since we're holding it in the circle, we're changing delta V, and that change in delta V, it's not a magnitude change, it's a directional change, and that leads to our centripetal acceleration. I think that's pretty explanatory, so let's move on. So we have a force holding something toward the center. In our case, in this case, I said that the tension was our force, but it doesn't have to be. It could be anything, right? It could be it could be your centrifuge or whatever, and the bottom of the vial is holding the material in a circle. So it doesn't matter. So we have a centripetal force, and it's going to be equal to our mass times our centripetal acceleration, which happens to point towards the center. Always points towards the center. Always points toward the pivot. Okay? Well, that equals our mr omega squared. Okay? Simple as that. All right? If you happen to have a known r correlated with a known v, you could rewrite it as v squared over r. You could do that. All right. Draw your free body diagram, okay? Draw it out. Here's my center. Here's the thing moving around, all right? And here's my omega. It's going in that direction. And I'm going to label things. Like I'm going to label this is negative. I'm going to label this as positive or whatever, okay? So you want to label your coordinates, draw your pictures. Don't, do it. It'll help you. I want to help you get all the points you can possibly get. A good let's say this is the sun. Let's say this is Jupiter, where boys go. So there's the sun, there's Jupiter, and Jupiter wants to go in a straight line, but it can't. So it's going in a circular direction. Why? Because gravity. So gravity is our centripetal force. How do I want to do this? I'll say mass of Jupiter, mass of Sun, and then we have to have the radius of the Sun, Jupiter squared times big G. I haven't put in any this is what G is, or the actual numbers for these constants. I'm going to give those to you. Don't waste your time putting those in. But at any rate, this is the equation, but that also happens to equal the mass of Jupiter times the radius of the sun to Jupiter times how fast it's angularly going around. Okay? So we can do stuff. We can take this equation right here. They're both equal to our centripetal force, and we can solve for stuff, right? We can solve all kinds of things. The mass of Jupiter goes away. And of course, somebody would probably have to give you the mass of the sun. And don't forget, I'm going to give you G, 6.67 times 10 to the minus something. I don't have it memorized. Whatever it is. And you can solve. It's an easy equation. You can solve all the stuff for it. So no problem. If I want to solve for centripetal acceleration, then that's easy, because this bit right here is my centripetal acceleration. So nice. The mj went away, so it's just the mass of the sun divided by the radius of the sun and Jupiter squared times g. Okay, so I mean these are quick, easy things. Okay, that you can do. How are we doing? I'm going to stop here, and we're going to call this one part B. So this is hold on. Okay. So what have we done? We have done part 1A already, and this is part 1B. And I'm going to upload them, and then I'll have part 1C in a second. See you soon.